So, with that all being said, my name is Nick Shrock, and I'm the founder of a company called Elemental that is new, and we are the stewards of an open source project called Dagster, and here to talk about that today. So, what is Dagster? It's supposed to say workflows for data applications, but I guess that's even more concise and pithy. But what we effectively are, we're open source Python API, and if you're familiar with a system like Airflo, which is used to orchestrate a DAG of compute, right? How many of you are familiar with Airflo as an example? Okay, so most of the room. We are, at first blush, we look quite similar to Airflo, but as I think if we go through the presentation, you'll see how it diverges from that system substantially. Let's see how this formats here. So, you hear all these terms, ETL, ELT, ML pipelines, data processing, et cetera, et cetera, et cetera. And one of the things that I find strange about this ecosystem is that, in my opinion, and in our opinion, all of these terms effectively comprise, they're all the same thing, right? If you look at an ML pipeline, actually, the previous presentation, all these great slides about how, very little of the work of an ML pipeline is actually, the actual training, right? All the work is all the stuff leading up to it, which is effectively an ETL pipeline. And in the modern world, the term ETL doesn't even make any sense. Because where did the term ETL come from, right? It came from way back in the day when you had one transactional system, then one transform step, and then you load it into a data warehouse. When people use the term ETL today, it looks nothing like that at all. It's a very complicated graph going through multiple different systems with multiple stages of materialization, and it's incredibly complicated, and there's tons of different people involved, right? It looks nothing like these old ETL systems. So all of this terminology feels very outdated. And then you have this discussion of is it extract, transform, load, or extract, load, transform? I can think of it's hard to think of a more meaningless discussion. Because this is all just like a caching decision, right? Like we're engineers, either you materialize it intermediate or don't, right? That's all that discussion is. So what we think of these are instances of what we like to call data applications. So how do I define a data application? How do we define it? They're graphs of functional computations that produce and consume data assets. And I mean functional computations in kind of a big sense, meaning that a Spark job is a functional computation, right? A data warehouse transform job is a functional computation. If you use a system like Papermill, a Jupyter notebook is a functional computation. And what a data application is a DAG that assembles these together in order to orchestrate something meaningful. So, what are the problems that we see in this ecosystem? One is, I think the developer lifecycle and development lifecycle is fundamentally broken in this system. So, my background is I was a Facebook engineer from 2009 to 2017. And while I was there, I built abstractions and infrastructure for our product developers. And so the thing I'm most known for is creating a technology called GraphQL. And effectively the team next to me was, hey, thanks. And the team next to me created React, right? So I don't have anything to do with React. I like to call myself React adjacent. When you go from that world, I was present at the creation of the full hipster stack. If you go from that world to this world and you see someone working in this, it's appalling, kind of the developer workflow, the lack of testing, the lack of aesthetics. There's all these individual brilliant systems that have achieved massive technical achievements in terms of being able to scale out. Big data is solved. It's amazing, But if you look at the developer lifecycle, it's broken, meaning that and comparing this to Airflo, say, you don't use the same tools in production that you do in local development. Local development with Airflo is not a thing. And testing is also not really a thing. Like, testing is really difficult in these systems, and so frequently people can only test these things in production. These systems are fractured and poorly understood, meaning that they're typically composed of a bunch of different technologies, a bunch of different type systems, a bunch of different metadata systems, and as the data flows from a data lake, my favorite term, no, the analogy betrays what a bad idea it is. You pour all the data into a lake, and then you can't organize it. It's perfect. It's the perfect term. So, as the data flow from these different processing systems, right, you effectively lose all context of the data. And if you, coming up to the system, are inspecting this graph, it's actually very, very difficult to understand what's going on, right? And these systems are typically authored by a bunch of different personas in this ecosystem. You have data scientists, data engineers, normal engineers, all participating. They're using different tools. There's no good integration layer to combine them. And then there's just tons of systemic repetition. And this is kind of difficult to express, but reuse is very difficult in those systems. And also, you just have this feeling, especially if you go to a conference like this, that everyone is rebuilding the same infrastructure over and over and over again. That's kind of, these are the problems we see. And so what do we think are kind of the values that we have that will help kind of move the needle on all these issues? One, predictably, that we think that the DAG, the graph of computations, should be participating in the full developer lifecycle, meaning that you're modeling this app and structuring it into computations. That should be how you work. Typically, right, how you work today is you're writing your individual job, and then only in the last second you plop it in this DAG that orchestrates with the other compute, and then you kind of like hope and pray it works. That doesn't make any sense when you step back and think about it. You should also be testing these graphs as you go along. Two, most of these workflow engines kind of conceptualize these things in terms of a DAG of tasks, right? Meaning that they only encode their execution dependencies. Task A, then tasks B and C, then task D. They're not modeled as functions. We believe in functional data engineering, meaning that these tasks should express and give guarantees about what their inputs are and what their outputs are. And then that embracing this multi-tool and persona world. I don't think the entire world's going to converge on Flink. I don't think the entire world's going to converge on Spark. I don't think the entire world is going to converge on one computational runtime. It's a heterogeneous world. It's going to continue to be heterogeneous. You have to embrace that and figure out a way to have an integration layer that incorporates this multi-tool and persona world. So this is one of my slides that got totally messed. But the another huge problem is the siloing aspect of this. Typically, in this multi-persona applications, in a lot of orgs, there's a strict dividing line between data science and data engineering. Meaning like, I'm the data scientist, I work in this tool set, and I'm creating models. And if I need data, I have to go over here and talk to the data engineer. This is what causes what some people call data breadlines. And that's not a particularly good situation. Where you want to get to is this kind of state where there's some sort of overlap between them enabled by tools and abstractions. This state of the world actually reminds me, I was at Microsoft 15 years ago, and back then there was a split where there's software test engineers, software development engineers. And the developers would write the code, and it'd be total piles of crap. They'd throw it over the wall of the testers, and lo and behold, there'd be bugs. And there's this crazy feedback cycle. Right? Looking back on it, it's actually kind of crazy. Now, what do developers do? We have unit test framework, we write tests, we're accountable for things. That's the way the world should work. In the same way, data scientists and other what I'll call data domain experts should be responsible more for the end-to-end capabilities rather than having these like these, instead of having the capability owned by a bunch of different people where there's kind of a dysfunctional relationship. So the claim is that the tools that we have are not equal to the complexity that we face. That's the claim. And this is like what DAGs end up looking like in these systems. It's crazy. And it falls apart so quickly. It's always amazing. We just see these type of DAGs over and over again. And then, I don't want to pick on Airflo too much because, like, I know the creator of it. He's good, and like the system has served us well. But it's also time to kind of, and they're trying to address this within the context of a lot of these things that we're saying in terms of functional data engineering etc., are trying to be addressed within the context of that system, but it has like fundamental properties I think are difficult to recover from. So what we want is what I like to call the full entire development lifecycle. So without further ado, I'm just going to hop in and just start demoing this thing. And we'll see how far we get here. There, are we good to go there? All right. So let's talk about develop here. Let's just hop to some code. All right. So now we see, bear with me here. Actually, I want to have that launch. All right. So let's go to like hello world here, and I'll make that bigger 1 second here. All right, so this is like computer science, blinking light demo, right? We're just like loading in some pandas data frame and doing some basic math, right? So we have a few nodes of computation. We're doing some math. So each solid, as we call it, this is kind of the unit of compute in the system. If you look at a graph, every single node is called a solid, all right? And each one of these things is just a function, right? Declares its inputs, declares its outputs. We have our own type system. We'll explain why we need that. And then this is just doing computation, right? And these are stringing together, doing some computation. In the end, we kind of do, combine two things. And then this is all strung together using this pipeline syntax. So this is this DSL, right? That this doesn't actually do the compute. This actually just builds a dependency graph, right? And because it's functions, we can just call them like functions. Functions are amazing. They like compose. You can pass things to them. It's this whole abstraction that works really well. So the moment we have the computations encoded in this format, we can load it into this tool that we call Dagit. All right, so let's load Dagit here. Sorry, I don't have much space for my mouse, so bear with me here. Here, can we see that? Yeah. All right, so now we can go and we can check out what this pipeline looks like, right? Not surprisingly, it's a DAG viewer. But I think the big distinction here is opposed to like DAG viewers you've seen in the past, this has a lot richer metadata associated with it. So it's not just, it's not just circles and lines, right? You can actually like inspect this thing and at least begin to understand what's going on. Let me go back here. So now we want to execute it. So one of the distinctions here between other systems and kind of the core difference between other workflow systems is that our DAGs are parameterized, right? You see here like the first DAG takes in a path and spits out a pandas data frame. Now, the issue with that is that it's not directly executable. You need to provide the parameters for this in order for it to successfully execute. And so we made the explicit decision to separate the structure of the graph from config, which can get complicated. So we have a strongly typed config system and help so you can kind of construct these computations for you. So if we go to what we call the execution pane here, let's imagine I hadn't written this. Now we have this kind of auto-completing config editor here, where it gives you like nice error messages. Because what we find, something fell there. Oh, it's fine. What we found is that so often these pipelines are just super complicated functions, and they end up just taking like balls of huge amounts of config, and it actually ends up being really complicated to manage them. And that's actually one of the things that prevent them from being testable. Because in order to have a testable thing, you generally have to kind of parameterize it in complicated ways. So now instead here, because this thing requires one input at path, we can say, hey, I need to parameterize this thing, comes from this input. This thing's really fun to use, actually, especially when the config gets complicated. And now I need to say, num.csv. Right, and this doesn't just provide value in this fancy pants editor. It gives you super clear error messages. So even when you're doing unit tests and whatnot, you can actually like debug this stuff super quickly. All right, now we execute this thing, and now we have this like live updating executor, right, where all your logs are right here. And this thing's really fun to use actually. And so this like serves as a local development environment. You'll also notice that our logs are not just raw strings. You can just log a raw string if you want, but I like to call normal logging just developers thinking aloud, right? And that's not nearly as useful as logging semantic information that is parsable by tools in a runtime. And so we'll go into how we do that. But like, for example, one of the values of our type system is that it does a type check, which is a function, but you can also yield meta information about the value that passed through it. It's totally user pluggable, but in this example, we do something simple where, let's say like, oh, I want to click on this multisolid. Okay, we just filtered down the events to that, and now we can see like, hey, at this input it had 2 row counts, and we can see what columns it had, and then once at the output it had these columns, et cetera, et cetera. So this is really useful for understandability and debugging. Let me go over here. So let's imagine I'm developing this. Let me zoom out. Guess I need to file a bug against the UI person about zoomed in stuff. But let's imagine I'm developing this and I screwed up, right? So there's DAG of compute, right? And then I raise an exception here. I am bad at programming or whatever. And I can't spell either. All right, so let's go back into this thing. This is too small to read, huh? All right, pardon the CSS bugs. So now we go in here. Oh, that looks fine. Is that big enough? Yeah? All right. So now let's re-execute this thing. So now we're going to get an error, right? And so this was a DAG, so we just display this in linear order because it's easier to absorb. But this one failed, therefore this one was skipped. You can go in here and like quickly get your stack trace and whatnot. All this stuff works the same in prod too, which is sweet. So one of the things that's nice is because we're aware of the inputs and outputs, and we can take responsibility for shuffling the intermediate values from computation to computation, we can also do incremental computation, which is super nice. So here, we can say, like, actually, what I want to do is try to retry this starting from where the steps have failed and skip the ones that succeeded, but shuffle the old values to the new run, right? So boom, now we do that. Now it's only going to try to execute 2 things, right? Specifically, let's go back here. Specifically these 2 ones. All right, let's go back to the runs. Go back here. Now let's say I go back and fix this. Where'd you go? Oh, there we go. Now I retry this. And lo and behold, it's fixed. Right, so you have this new debugging flow. Yeah, what's up? Correct. Yeah. So one of the things is that we shuffle intermediates, and it's pluggable too. So in a cluster, it'll store an S3 or an object store, but locally we're doing it on the file system, right? Okay. Where am I at here? So we have all these fun development tools here. Now let's talk about testing, right? I showed you the UI, but it's like, listen, like, am I going to work in UIs the whole time? Show me code. I'm not going to explain this slide. All I'm saying is that, oh God, this got messed. So ignore this code. The whole point is that you can actually unit test these pipelines. Like, there's a Python API where you can parameterize them and execute them. We can plug the environment so that in a unit test environment, we're not persisting the runs meta information to a database, just like an ephemeral thing. Contrast this to Airflo, where like in order to run Airflo locally, like you have to like be touching a database the entire time. It's actually really difficult to run tests in isolation. So productionize. Let's see how bad this is. So this is probably not visible really. The point of this though is that the goal of this system is to make it so that people writing domain logic are effectively just writing their business logic. And then these units of computations, these functions, are queryable by an API, meaning they're metadata, and operable by an API, so that you can write an entire suite of DevOps tools around this. So all this is doing is actually like newing up an EC2 instance for you, newing up a database on your behalf, and then uploading this thing to AWS. But this is just the beginning of our journey to really operationalize and make this kind of a programmable infrastructure to deal with all your DevOps issues. I'm going to skip this for now. Where are we at? 522. All right. And then we also provide a scheduler. So you can define your schedules in Python. And I should probably stop picking on Airflow too much. But what Airflow does every 5 seconds, it evaluates a file and constructs every single DAG and then decides to schedule it or not. We take a different approach where we use cron. Cron works. It's worked for I don't know since before I was born. And all we do is say we have cron point to a function that says construct this pipeline, provide this config, and then run it. And then we also provide a Python function so you can filter out events on like English bank holidays or whatever. And it's a very simple, reliable system. It isolates the pipeline construction from other pipeline constructions. It ends up being just a much more reliable way to structure your computations. All right, let's talk about testability for a second. And what do I mean by it? Oh God, this got totally messed up. So this is what we see in the status quo today, where very little of these computations can be tested in a unit testing context, and then maybe there's some integration testing, but really you just kind of like push and pray usually. Maybe you have a staging environment if your DevOps people are really good and you really take time to do that. The one thing I think that happens is that testability people come in here, and this might trigger some people in this audience, but they often come in and they're way too ideological about testing, and you start getting like lectures about mocks and stubs, how to like mock stub fake, like let's please can we move on to something else? But the idea here is that we want to take traditional testing techniques and apply it to this domain, and this domain is hard, right? You don't have control of your inputs typically, you're just getting it from somewhere. Your business logic is typically encoded in centralized services that are impossible to mock locally, right? Like Spark, you can't mock. Like that would be an entire company to like mock Spark. Like you don't want to do that. But there are tons of stuff in these systems that can be caught by unit tests, and they should be caught by unit tests, right? DAG structures, configuration parsing. There's some business logic which can. It's just a question of how to restructure your code. But the corollary to that is what I was explaining before, is that don't attempt to unit test for errors that you can't. Striking this balance is difficult, but I think it is critical to moving the needle on these systems. And like what the attainable goal here is to make it so you can kind of move a bunch of the testing upstream. But this shifting the curve to be like this represents like an order of magnitude increase in productivity. Because the more errors you can catch up the line, the faster your feedback cycles or whatnot. But like, you're always going to have some testing in production, as an example, because some errors in this domain cannot be caught until production. For instance, if the inputs change underneath your feet. So like part of this is that you have to have tests in production to test your data quality. You should think of this like a factory, and like in any stage of a factory, there's QA. All right, I have 5 minutes. So Airflow, as I mentioned before, doesn't really address develop and test, only like productionizing and scheduling these things. So what do you need to actually make these systems testable? One is your actual system environment needs to be pluggable, meaning that the primitives provided by the system. Like if you have a dependency and production on S3 to do intermediate shuffling, you have to figure out a way to make it so it's executable on your laptop in a CI/CD pipeline. You also want to provide an abstraction for pluggable user environments, meaning environmental context that the system cannot know about, that only the user in their particular domain can know about. And then you also need parameterized computations. I know that was a lot, but and I'm kind of jumping around here. So let's talk about metadata. So as I said, this is our system, and just to contrast what this DAG looks like in comparison to Airflow's DAG here, is that this has like, descriptions, types, you can kind of get a sense of what's going on. We actually have a first-class compositing abstraction, because meaning that it's a function, so functions can call the functions. It's this whole thing. Contrast that to DAGs and Airflow or Kubeflow or any of these other systems, and there's generally like no meaningful metadata there, right? It's just like boxes and arrows, right? All it's expressing is the how of the computation. In what order do you compute? Rather than like what that computation is doing. It's kind of the difference between the systems. It's like, this is why we like calling it an application layer. Yeah. So yeah, the outputs are optional. So what you can do is that you can think of the outputs like an event. And like sometimes an event doesn't fire, and then that entire downstream DAG is skipped. So we do have some dynamic control flow constructs implemented through that mechanism, but it's not fully Turing complete or something. All right. Oh, you're right. I need to switch to my other deck now. Yeah, this was a whole mess. So just like summing this up quickly, you know, and this is all compressed and weird, right? That's fine. So, you know, typical data applications here are cross multiple system barriers and then frequently have multiple different constituencies, right? So you might have data engineers running a Scala Spark job, then the analysts, if you're lucky, are writing SQL statements to do their business logic, maybe in a tool like dbt. If you know, who knows dbt here? Anyone? dbt is a great tool. Everyone check it out. And then data scientists maybe pick that up. You know, Dagster simply effectively wraps these computations in this unified metadata layer, and then if you kind of go full on, meaning like you're starting to use more of the Dagster native constructs to in your Python code, and all the computations are structured as solids. So we're building an ecosystem here. So there's a center graph, which is the center of everything. Below it is arbitrary data processing tools, any storage, any language, any runtime. By I mean any language, like the Python can shell out to anything, right? On top of that, we have Dagster native tools built over an API. Spoiler alert, that API is GraphQL. But that doesn't even matter, right? We have these nice tools on top of it, and because it's an API, you can also build your own tools. Right? We provide local development, monitoring, the config editor, all that stuff, right? And then also on this tool, we have integrations with existing infrastructure tools. So this is a pure software abstraction. It's meant to be able to be deployed across any arbitrary execution substrate. So it's not vertically integrated and tied to, say, Kubernetes, like Kubeflow, right? So you kind of have, we're building this ecosystem here. We have arbitrary computations underneath the abstraction that represent different constituencies. They all collaborate to build a single graph of compute that's accessible behind an API. This is how we build our local tooling, doing our local executor, but we can also do things like, oh, this is supposed to be Dask, but we can compile actually to other task formats. So we have like an API format that allows you to, in your Airflo DAG, like just call a function which invokes one of our pipelines with a configuration. It constructs an Airflo DAG on your behalf. We can also do the same thing with like Dask, for example. And let me see where I'm at here. I haven't seen this one in a while. So anyway, I'll close this out. But you know, this is an open source project. It's on GitHub. You can check it out. We have a Slack, you know, all that stuff. So if you want to experiment with this, let us know. Sign on. And thank you very much.